Welcome to Finite Element Methods. We'll be discussing axisymmetric elements, which are two-dimensional elements. We, in a previous lecture, discussed plane stress and plane strain, but today we'll be hitting the axisymmetric elements, which are a type of 2D elements. So what are axisymmetric elements? The problem in these cases are going to involve an axis of revolution. So in general, you're only modeling the cross section of the wall thickness, for example, and that wall thickness is revolved around this axis of revolution. So you only have to really model this cross section, and basically you're going to discretize the domain using triangular elements or quadrilateral elements, but this element behavior is simulated in such a way that it can represent the 360 behavior of the structure. The boundary conditions in these cases are symmetric about Z. So all the boundary conditions are independent of the circumferential coordinate system. All loading conditions are symmetric about Z. So if I apply pressure here, that pressure is getting applied 360, for example. And independent of they're going to be independent of the circumferential coordinates. Finally, the material properties are also symmetric about Z. And we're going to then, in general, when you have a 3D structure that can be represented by a single cross section that can be revolved about Z, all you have to do is to model that cross section. And we already done few modelings like that. You can find some video tutorials of axisymmetric modeling, but today we'll be covering some of that theory so it's clear. How we're going to deal with that? So axisymmetric formulations are such that the strain deflection relationships for axisymmetric models are such that the derivatives with respect to theta, which is the circumferential coordinate system, is zero. The strain deflection relationship is going to look like that. So if this is the axisymmetric elements, the deflection in the radial direction is u, and u is going to depend on the the radial coordinate, and z is going to be the axial coordinate, which is along the axis of revolution. W is a deflection in the z direction as well, while u is a radial deflection. The strain displacement relationships for axisymmetric elements is given by these equations here. What you see here is a strain in the radial direction along the u direction. Epsilon theta. Theta will show up, is not zero, and is going to be in the circumferential uh, coordinate system. Epsilon zz is the strain in the z direction, and epsilon rz is a shear strain, which is the angle change between r and z coordinates. So what you see here is epsilon r is the partial u respect to r, epsilon theta is u divided by r, epsilon zz is partial w respect to z, epsilon rz is a partial w respect to r plus the partial u respect to z. And this right here can be written as this matrix that you see here. Partial respect to r times u gives you the first here, the first term here. And then this row times column is 1 over r times u is this one. And then this row is partial of w respect to z, that's this one. And then this one goes with u and this one goes with w. You can see I recover that. So this derivative or operator derivatives is going to be very convenient later on. And we're going to call this L bold and then this column vector U bold. The constitutive law will relate stress to strain in this manner. So that's a constitutive law that we derive for plane strain elements, and it makes sense to use it here for axisymmetric formulation because in the circumferential coordinate system is basically infinite. I can keep going around and around. So this constitutive law is more similar to plane strain formulation. And these strain deflection relationships you see here may not be familiar to you, but they're derived in more advanced theories. They're also derived in my book, But for now, we're going to just provide those relationships instead. The equilibrium equations are quite simple as well. You can see them here. Notice how sigma RR is going to be the stress in the radial coordinate. Sigma RZ is a shear stress, which changes this angle here. And then we have sigma RR minus sigma theta theta. And sigma theta theta is a stress in the hoop direction. And that's divided by R. And again, that's the second equation as well here. So we have three unknowns, and then we have two equations. Okay, so we have to figure out a way of solving these equations. The total potential energy of the system under applied loads is given by this, right? We already covered that for the three-dimensional case. This is the equation that gives you the total potential energy. Notice that the total potential energy of the system depends on U, V, and W. That's in the most general sense. U here is a radial coordinate. W is the axial deflection. Sorry, U is a deflection in the radial coordinate. W is a deflection in the along the axis of revolution. We cover that. And V is a circumferential deflection, which we're going to assume is zero in our case. So here we have the body forces and then the traction loads applied. For an axisymmetric behavior, the total potential energy simplifies further. So we don't have uh, this term right here, and we don't have this term right here. So those go to zero, and then all you have is these four terms that you see here. And notice how the dv here becomes 2 pi r dr dz. And that can be very easily derived. So that volume integral can be broken up to be 2 pi r dr dz. And that's a very simple thing to check, and that is the case for dv. I can break up dv into that. And then every integral will also have that 2 pi r dr dz. And then this integral is a line integral. And we already covered that. So ds is a surface, this surface right here. But since we're only looking at two-dimensional, this becomes a line integral, this curve bounding that surface where tractions are applied. Body forces are a volume quantity, and so that's why you see a dv there, and that dv is 2 pi r dr dz. I can write the total potential energy in a simpler form. So sigma bold times epsilon bold. We'll cover that. Sigma bold is this stress vector. Epsilon bold is this strain vector. I can take this row vector times this column vector, and I can then determine that that's a scalar quantity. Pi over an element is only dependent on the deflection, the two deflections, the radial deflection and the axial deflection. B bold, U bold is these two quantities right here. So you see them here. T bold times U bold is a quantity we just discussed right here, but V is zero. And I can have point loads like Q bold times U bold, and this is calculated over an element. Again, this is L bold times U bold, the strain bold, and C bold is the constitutive law. So now all I have to do is plug that in to pi, the total potential energy. So if I choose an approximation function for the displacement field, Q bold is U1, W1, U2, W2, U3, W3, and I can have M nodes. So every node is going to have 2 degrees of freedom, which represent the two deflections, the radial deflection and the axial deflection. You can see here very quickly that can approximate U and W over the domain. And I have here a block of N1, N2, N3, and so forth. The first row times that column vector gives me U equals N1 times U1 plus N2 times U2 plus N3 times U3 and so forth. That will give me the approximation for U. For W, the approximation is N1 times W1 plus N2 times W2 and so forth. You can see that we've written this in such a manner that allows us to approximate U and W over the domain. And this does a good job. Here, the the ends are your shape functions, the trial functions that we're using in the Rayleigh-Ritz approximation, or the Ritz basis functions. So this becomes your N bold, this becomes your Q bold, and now I'm ready to plug in the equations into a total potential energy. So this is what we got so far. And now what I have is that U and W are N bold and Q bold. We're ready to substitute everything in here. And notice how stress equals the constitutive law times strain. But strain, we already know that strain equals L bold times U bold. So you have C bold, L bold, and U bold for stress, and then L bold and U bold for just strain. And so I continue here, U bold, B bold. So that stays like that. I have U bold and T bold and so forth. And now I can substitute what U bold is. U bold is M bold, Q bold right here. And again, U bold is right here, Q bold, M bold. And then U bold is Q bold times M bold. So that's what we got so far. And finally, uh, I'm able now to extract Q bold out by applying the transpose over these things. And this is what I get. Now I realize I have this L bold times M bold. I'll call that B bold, and that will simplify the problem quite a bit. Again, L bold is this matrix operation here, this operator, and M bold is this matrix right here of shape functions. So I'm ready now. I can rewrite the potential energy, total potential energy, like this. So the Q bold does not depend on the volume. So I can put it outside of these integrals, as you see. And I'm doing that everywhere. So this one here, this one here, and this one here. I can now minimize the total potential energy as discussed before. So partial pi respect to Q bold, and that's equal to 0. And so then this 1/2 Q bold transpose goes away. And so it ends up like that. So therefore, the axisymmetric element formulation just happens to be this right here, very simple. And I want to solve for Q bold. That's my goal. Body forces could be provided, traction forces could be provided, the shape functions are known. So all these integrals are known. B bold is known, C bold is known, B bold is known. I can integrate that. The only thing that's not known is Q bold. And like I said before, every triangle element here is going to have different shape. I need to find a way of having them all the same shape. So I'm going to use isoparametric formulation. And the idea there is that I'm going to approximate the coordinates now, which are R and Z. I'm going to approximate them so that when I plug in C and eta here, that when I plug it in here, I get the value of R and Z. And C and eta are going to be in the standard element formulation. So what I get is that this is equal to this matrix of shape functions. C bold is this column vector here. And this is equal to M bold times C bold. And again, these ends now are defined in the standard element formulation, in the one which I'm calling the master element, which are defined in the C and eta coordinate systems. So with that, for triangular elements, N1, N2, and N3 are given by these equations here, these shape functions, which are the basis functions. And the cool thing is, when I plug in the value of C and eta here, I'll recover the value of R and Z, the coordinates, at those different nodes. If I plug in the C and eta corresponding to the nodal location. So we know that one of the nodes are in the standard element is psi and eta equal to 0. So if I put 0 here and 0 here, that's 0, that's 0, I get n1 equals 1. So I put 1 here, 0 here, 0 here, and so forth. What you'll find that this row vector times c bold will give me that first node. And that is a point. For a triangular element, that's all you have. So you have, it ends up to here for a triangular element. For a quadrilateral element, which is 4 nodes, I will have a block of 2 more, n4, 0, 0, and 4. That's what I get. The Jacobian can be calculated. Partial of r respect to psi, partial of z respect to psi, partial r respect to eta, and this Jacobian is the one that gives me the ability of connecting the standard element into a generally shaped element. This is your transfer function. This contains the geometry information, is one of the few things that contains that information. And we already derived the shape functions for quadrilateral elements. The isoparametric formulation then becomes this very simple equation for quadrilateral elements. The integrals will go from -1 to 1 because in the quadrilateral element is mapped to a square which goes from -1 to 1, -1 to 1. And you can see I have this 2 pi r that shows up from the integral because it was a volume integral, dip c d eta. Now I have this determinant of j, and then I have this is equal to the rest of this stuff. Again, integral from -1 to 1 for the body forces. Now, what you realize is that B bold requires the calculation of these derivatives. These ones here, I'm sorry. Partial of n with respect to r for each of the shape functions, I equals 1, 2, 3, 4, and so forth. These derivatives need to be calculated, but you can see that n does not depend on psi or eta. Sorry, do not depend on r or z, but they depend on the standard coordinate systems. As a consequence, to take this derivative, I have to do something. So how do I do that? I have to somehow take these derivatives, and I have to find a way of doing that. So what I'll do is do chain rule like I've done before. And by doing so, I'm able to then uh, calculate these derivatives by inverting Jacobian here. And I know these quantities because I know n as a function of c, I know n as a function of eta. So these are known. I know the j here, so invert that to get these derivatives. And I've done this here. This is fully known, this is fully known. Then I can calculate these derivatives, which are required. You can see here that is required. You can see that I have to calculate B bold. L is the operator of differential operator, and I have to apply that to N. And so if I look at a single block, B1, B2, these are the different blocks. If I choose a random one, BI, then that's going to look like this. And you can see here that to calculate these quantities, which can only be found by calculating this Jacobian, inverting it, and multiplying by these quantities are known. That's the way I can find these values and plug them in here. For a triangular element, it's the same thing, but now the integral goes from 0 to 1 minus eta, and eta from 0 to 1. And that's how you'll do a triangular element. But basically, that's a procedure. Same thing for quadrilateral element. For triangular element, it's just the integral now goes over a triangle rather than a square. The axisymmetric isoparametric formulation Abaqus uses the CAX4 element, which is quadrilateral. That means axisymmetric. And CAX3 elements to implement the axisymmetric elements. In Abaqus, the axisymmetric formulation uses the following coordinate system. The axis of revolution is about y, which corresponds to the z axis in the formulation I just discussed. So I don't apologize. That's the way we did it, and that's the way they did it. So it's just different. The axis, the x-axis corresponds to the r radius. R equals 0 in the formulation represents x equals 0. So r equals 0 represents x equals 0. And the model in Abaqus has to be constructed so the axis of revolution is about the y-axis. Just keep that in mind. Let's look at how we could apply these forces um, to an element. So with no body forces, we need to figure out how to apply this pressure applied to this edge 1, 2, for example. So that integral has to be calculated. This integral has to be calculated along this edge 1, 2. And the pressure is acting in the radial direction, so that's why you see a P here. No traction applied on this surface in the Z direction, so that's 0. And I have to figure out how to calculate this ds1. ds1, notice how this edge will get mapped to C, okay? So I have to figure out how to do that. The one thing I want you to realize is that this 2 pi rp, where a radius, this is a radial location where the pressure is being applied. In this case, we have to determine where that radius is and plug that number here. The rest of it is just simple. This dip C and this partial of R respect to C, partial of Z respect to C. We already covered that on how to do that. This is evaluated at eta equals -1, and in this particular edge. How do I know that? So if this is 1 and 2, that's 1 and 2, right? In our standard element. So on this edge, C is the one varying. That's why it's deep C here. And then RP is this distance from here to here. So that's fine. And then eta equals -1 because we're looking at this edge, which is eta equals -1. So this is how you formulate the axisymmetric isoparametric formulation, which is very useful for for example, this right here is a single element, but that represents a 360 ring of that particular behavior of that element. So that's how that works. I hope you enjoyed this particular lecture. We already did some tutorials on that, but it's worth understanding the theory behind it. You have a great rest of your day.